Okay, welcome to today's class. Before I start, I'll probably have more details on this later and possibly in the form of an email so we can keep it all straight. But I do want to remind you about the next exam review, which is going to be, believe it or not, coming up fairly soon. Not this Friday, but next Friday, so don't get too panicked. But that would be the 19th, I believe. So Friday, April 19th, we'll have an exam review from 1 to 3 p.m., or hopefully not that long, but at least an hour and a half or so. And that's going to be same story as before, 1 to 3 p.m. in this room. So I should have the problems for that posted by the end of the week. And I'll have to double check also where exactly the stopping point is for this exam, because it only covers part of Chapter 9, not the whole thing. And I have to remember, I think it's 9.5 is the section number, and that'll be a topic that we'll probably get to on Monday of next week. But I'll double check and be more clear about that next week when I get to it. And then the final exam review, we will have sort of split up between class and a separate session. So we'll have on the 26th, which is the week after this, more details to follow. We'll have another review session for the final, but that'll only be part of it. The rest of it we'll do in class because we are going to be able to wrap things up. The new material will be wrapped up in advance of that. So I need to open my pointer. All right, so let's get into it then. I messed up a little bit when I made the notes. I duplicated some slides in this set of notes that we'd already had in the last set, but I guess it's not a bad thing to go over things more than once. And I'll just quickly go through these first few, which we covered last time. So if you were here and you were in a reasonable state of consciousness at the end of last class, you would have seen this stuff already. And we'll go through it again, but again, not in as much detail. So if you want to remind yourself more about these, it'll be in the last class that we covered it. So what we're moving into in Chapter 9 is a discussion of what are called condensed phases. So we talked about gases in Chapter 8, and most of the time we were talking about ideal gases. And the key assumption of ideal gases, which are governed by the kinetic molecular theory at the atomic level, is that the gas molecules have no interactions between them. All right, so in order for things to behave as ideal gases, this has to be true. And by interactions, we mean forces of attraction primarily, or repulsion as well. So really, the gas molecules don't see each other at all. They're just sort of randomly colliding, but not interacting in any sort of meaningful way. Now, what we saw, though, at the end of that chapter with real gases, and what we're going to be talking about a lot today in the context of liquids and solids, especially liquids today, is that there are actual interacting forces, attractive forces primarily, So in gases, these forces are pretty weak, but they do sometimes, at certain conditions, result in deviations from the ideal gas law. So when we talked about real gases and how they don't exactly follow the ideal gas law, it's because of these intermolecular forces. That's primarily the reason for that. And then when you have liquids and solids, those types of forces are often important in holding those together into those condensed phases and preventing the molecules from just escaping and going off into the gas phase. So that's kind of the sort of transition between Chapter 8 and 9 is moving away from the idea that molecules have no interactions with each other, and actually now talking about the fact that in reality they do, and these are very important, especially when you're talking about liquids and solids. So we call these interacting forces intermolecular forces. Remember the prefix inter means between, so these are forces. These are all attractive forces, by the way. We don't really have to worry about repulsive interactions in this context. So these are forces of attraction, and these are between two molecules. All right? So we're no longer talking about the forces, the chemical bonds that hold molecules together. That was a topic we covered a long time ago. We talked about ionic covalent bonding, all that stuff. Now we're talking about forces that are between two different molecules. So if we have two water molecules, how do they interact with each other? Or any two molecules, really. So we have to keep in mind that these have nothing to do with and just to more briefly say it today than I did last time, these have nothing to do with chemical bonds. So we're not talking about overlap of orbitals and sharing of electrons and all that stuff that deals with chemical bonds. Of course, that's still there, but that's not what we're talking about in this context. When we talk about intermolecular forces, we're talking about much weaker interactions between two different molecules that each individually held together by chemical bonds, but now we're talking about how those two are interacting with one another. All right, and then what we're going to often talk about these intermolecular forces, one of the contexts that we're very often going to see them in is in phase changes. And we can already start to appreciate the fact that as you go from gas to liquid to solid, the intermolecular forces tend to become stronger and stronger. So in gases, there's basically no interaction or they're very weak, and that's why the molecules are able to fly around pretty freely. But in liquids, the molecules, even though they're in contact with each other and they're not in the gas phase, they do have a significant amount of motion associated with them. But then in solid, the atoms and molecules are held pretty tightly, so those would typically have strong intermolecular forces. And then talking about how these phases interconvert is going to be something that we'll come back to at the very end of this chapter in more detail. But essentially we want to know at least the terminology to start with. So we talk about liquids and gases and those conversion. If we go from liquid to gas, it's called either boiling or vaporization. And then if we go from gas to liquid, we call that process condensation. And then liquid-solid conversions we talked about as well. Going from a liquid to a solid, we should be familiar with this from our everyday life. It's called freezing. And then going from a solid to liquid, it's called melting. All right? So those are the phase changes that deal with when these different phases convert between each other. And a key point that relates intermolecular forces to phase changes, why are these two even related at all, is that the stronger the intermolecular forces you have, we're going to abbreviate intermolecular forces as IMFs, that's going to correlate with a higher boiling or freezing point. So boiling point and freezing point are the temperatures at which these conversions happen. There's more precise definitions for that coming later. But essentially, if you have stronger intermolecular forces, you have to put more heat into the substance, higher temperature, to cause those forces to break up and to cause these phase changes to occur. Because whenever we're doing a phase change, if we're going from liquid to gas, we have to break intermolecular forces to cause the molecules to separate from each other into the gas phase. And if we're going from solid to liquid, we're not completely breaking the intermolecular forces, but we are disrupting some of them that are holding the atoms and molecules in place. And so all of these phase changes involve either breaking or forming intermolecular forces. And if we're going to break those intermolecular forces, we have to put heat into the system. And the stronger those forces are, the more heat we have to put in. So this hopefully makes sense, at least at a conceptual level. And then what we're going to start with today is how to classify the different types of intermolecular forces. So there's not just one type of intermolecular force. There's actually a few different categories. And which ones actually are important depend on the type of substance we're talking about. All right, so we're going to go through, this is all new stuff now, so I kind of blew through the stuff that we already covered last week. Now let's get into what's going to be new for today, which is classifying the types of intermolecular forces. And the first one we're going to talk about is London dispersion forces, sometimes just called dispersion forces. The London term is not always included, but if you see any combination of London or dispersion, just treat them as the same thing. There's only one thing that has this sort of terminology. And the question is, we're going to primarily be talking about these intermolecular forces in the context of covalent compounds. So those are going to be either non-metal elements or compounds made up of exclusively non-metals. Those are where these typically are dealt with. And so what types of compounds have London dispersion forces? The short answer to this is that all of them do. So it doesn't matter what kind of compound you're talking about, there will be London dispersion forces present as one of the intermolecular forces involved. So anything that has electrons, which I think is any chemical substance in the world, will have London dispersion forces. All right, so this is present everywhere. So even in gases, there's going to be London dispersion forces, although they're very weak, as we'll see, but they are always there, no matter what type of substance it is. And sort of how do these arise? The origin of these is kind of a little bit complicated, or not something that we're used to thinking about, but they involve what are called instantaneous dipoles. And we'll sort of give us a couple pictures of what that means here in a second. All right. So we've talked about dipoles in the context of individual bonds and molecules, how if they have a dipole, that means they have an imbalance of charge, an unequal distribution of charge. But these types of instantaneous dipoles can even occur in things that are rigorously nonpolar. So let's say we have helium. Helium is just a single atom. Of course, we can't think of that as being polar because it's just one atom. It doesn't even have a bond. But if we have two helium atoms, remember, on average, the electron density in a helium atom is spherical. The valence electrons are in the 1s orbital, which is spherical. So on average, they're going to have perfectly symmetric spherical electron density. However, as we talked about in quantum mechanics, you're going to also have these are sort of probabilistic models. It's not that the electrons are always going to be exactly arranged in a sphere around the molecule. They're going to be moving around. They're going to have some probability of sometimes being further away to the nucleus, closer to the nucleus. So at instantaneous periods of time, you're going to have unequal distribution of the electrons sometimes. Again, the average is still totally symmetric. So let's say at some instantaneous period of time, you have a helium molecule where this little circle is representing electron density. Let's say the electron density at some instantaneous period of time is on average further away from the nucleus over to the left of as I've drawn it. This is going to then interact with another one. So in this case, you would have a partial positive close to the nucleus and a partial negative farther away, the electron density no longer being symmetrically distributed for this instant in time. Remember, these are instantaneous dipoles, they're not permanent dipoles. And then this can interact with another atom that's sort of polarized in the opposite direction. That would have a partial negative facing that way and a partial positive facing that way. And anytime two oppositely charged things come together, they have an attractive interaction. Now, as I said, this is very weak because this unequal distribution of charge that would exist in something like helium is only going to occur for very brief fleeting instances. So it's not like they're permanently unbalanced and have this really strong interaction, but at periods of time you're going to have that. And then again, this is a sort of a fluxional process, so you're going to also have sort of the opposite polarization as well. And it's not just staying in one place, it's moving around. So you can also have delta negative delta plus on that side, delta plus, delta minus interacting in the other way as well. So this is, again, a sort of a dynamic process where these charges are constantly in motion, and at periods of time they're going to be imbalanced and cause these types of interactions, albeit very weak. All right, maybe perhaps a better way to visualize this, or sort of a complementary one, is to look at molecules. So let's say we have a Br2 molecule. And as we talked about back in Chapter 3 and a little bit also in Chapter 4, this molecule will be completely nonpolar because it's two of the same atom bonded to each other. They have the same electronegativity. So on average, the electron density in this molecule is going to be symmetrically distributed between the two bromine atoms. There's not going to be a permanent dipole or a permanent imbalance of that electron density. So if we want to draw the electron density, it would be a little bit more oval-shaped in this case. So you have sort of this symmetric oval-shaped electron density, and then you have another Br2 molecule with the same thing. Let me draw that a little bit smaller. It's going to be hard to fit all this. So you have a sort of symmetric distribution of electron density around the two bromine atoms, another one that is basically identical, symmetric distribution. But then at some period of time, let me draw little arrows there to indicate that this is sort of a time progression that we're showing. At some period of time, you could get an imbalance where, again, because of the probabilistic nature, or what's called the polarizability of electron density, it's not always going to be staying in the same place. It's sort of in motion all the time, and sort of what you're looking at in a probability model is the average. And so at some period of time, you're going to have an unequal distribution where there's, let's say, more electron density on the right-hand bromine atom. So we're going to distort it in that direction a little bit. You're going to get a small partial positive on that bromine, a small partial negative over on this side where the electron density is unbalanced, again, for just a brief moment in time. And then this can interact with another molecule that's polarized in the opposite direction. So if we have another molecule down here that's going to be, let's say, polarized this way with partial positive there, partial negative over there, those opposite charges can sort of line up with each other and interact. So again, you get these sort of instantaneous dipoles that interact in different ways, and we can polarize it in the opposite direction as well. So it's constantly dynamic. It's not stationary, not permanent, but you get these small interactions because of this. All right, so even in nonpolar substances, you have these instantaneous dipoles, these imbalances of charge, and so you get delta minus, delta plus, delta minus at some instant in time, and those are going to cause a weak interaction for that instant in time. All right, on average, they're nonpolar, so on average, the electron density is symmetric, but they are going to distort over time, and during those distortions, there can be weak interactions involving those instantaneous dipoles. So that one's hard to visualize, but at least for the types of things we'll ask you mostly, you just have to recognize that every single substance has these types of interactions. Right? No matter what it is, no matter what kind of compound or element it is, it's going to have London dispersion forces as an intermolecular force. So really, the intermolecular forces for a substance are going to be often a combination of more than one. If it's going to be a single element like helium or a nonpolar molecule, this will be the only one that's present, the only type of intermolecular forces, but there are other ones that can also contribute. And really what you want to think about and we'll get some problems like this later on today, is when you're classifying a particular substance, you want to always think about what's the strongest intermolecular force that's present, because that's going to be the one that dominates the key properties that you're interested in, is whatever that strongest force is. So intermolecular forces are weak, but in some types of substances, like primarily the elements that are nonpolar, or any sort of nonpolar substance, this will be the only type of intermolecular force that's present, so those are relatively weak. All right, so then let's talk about how do we classify how strong the London dispersion force is. And so we can sort of understand this a little bit by looking at the boiling points of noble gases. So remember we said that the stronger the intermolecular force, the higher the boiling point is going to be. And if you have a noble gas, helium, neon, argon, krypton, xenon, and radon, that's the only intermolecular force that's going to be present. You only have London dispersion forces because these are nonpolar substances, okay? So if we look at the boiling points of these, even though they all have just one type of intermolecular force, which is the London dispersion force, the boiling points are not the same. So we start with helium, which has a nice toasty 4 Kelvin boiling point. So that means it's a gas at any temperature above 4 Kelvin, which is very cold. I wouldn't suggest subjecting yourself to that. If we go to neon, which is the next noble gas, so basically we're going down the noble gas series from lighter to heavier, down that last column of the periodic table if you have one in front of you. Neon is slightly heavier than helium, and its boiling point is 27 Kelvin. And as we go down the column, we see a progressive increase in boiling point. So 27, 87, 121, 165, and then radon, which is the heaviest noble gas, still a gas at room temperature. So room temperature, remember, is about 298 Kelvin. So still boils below that, so it would be a gas, but it has the highest boiling point yet. So what we see then is that if the boiling point is increasing as we go down the column to heavier and heavier elements, that means the London dispersion forces, their strength is increasing in that direction as well. So we can conclude then that London dispersion forces are stronger when there are more electrons present. So most of the comparisons we'll use for London dispersion forces are going to be basically whatever has heavier atoms or heavier molecules, whatever has a higher molar mass. Those will be the ones that we would predict have stronger dispersion forces. All else, as long as they're all nonpolar molecules, and London dispersion forces is all we're comparing, the heavier the atom or the molecule, the stronger the London dispersion forces are going to be. Now, why is this? It's because of what's referred to as the property called polarizability, which is the ability of an electron cloud to distort. So remember that for these London dispersion forces to occur, the electron cloud has to distort a little bit. It can't be perfectly symmetric and nonpolar. It has to distort for a brief period of time and create an instantaneous dipole. And the ability of that electron cloud to distort is called its polarizability. And then the other one, so then what this means then is if you have larger atoms, so heavier atoms with more and more subshells involved, the outer electrons are going to be held less and less tightly. Remember we said that as you go down to the periodic table and fill up increasing principal quantum number shell numbers, those are further and further away from the nucleus. So the electrons that are further away are not held as tightly, and they have an easier time distorting and sort of moving around. In this, they have what we call greater polarizability as a result. So outer electrons are held less tightly. in larger atoms. So this is sort of the reason why. So you have outer electrons that are held less tightly as we get to heavier and heavier atoms, and so heavier atoms are more polarizable. And the more polarizable something is, the stronger the London dispersion forces will be. Now there's one other aspect of London dispersion forces that I want to cover before we move on from this topic, which is, and I don't think I have anything, so I'm just going to spitball real quick. So one thing that also matters for London dispersion forces, and we're going to only sort of do this evaluation for one particular class of molecules, is the shape of the molecule itself. So the context that you'll see this in is, let's say we have two isomeric hydrocarbon molecules. So let's say one of them has this structure here. So let's say so it's 5 carbons and 12 hydrogens, C5H12, and then another form of that would have this sort of linear form. All right, so if we're comparing two molecules, these have the same molar mass, same chemical formula, same molar mass. One thing you're going to want to be familiar with in this section of the course also is that if you have a hydrocarbon, something with just carbon and hydrogen in it, it's going to be nonpolar. So any of these are nonpolar. So these are both nonpolar molecules, which means that London dispersion forces are the only intermolecular force present. In which of these do we think London dispersion force is stronger, left or right? Right. And any reason why? So yeah, it does have to do with the shape. So when you have a linear molecule, remember that these London dispersion forces involve contacts between two molecules. In a linear molecule, you have sort of a wider contact between the two, whereas this, which is more sort of spherical shape, you can't get as much interaction. So if you had two molecules like this, they'd be able to line up pretty well. I'm not running out of room to draw this. And those instantaneous dipoles will have a lot of points of contact between them as these molecules sort of line up with each other. Whereas a spherical molecule, you can't get them as close to each other and pack them as efficiently. So the shape of the molecule also matters. So this one here is going to have stronger dispersion forces than the one on the left. All right? So I just wanted to point that out quickly because you might see some homework questions that involve that concept as well. So in most cases, we just look at molar mass, but in cases of substances that have basically the same formula, same molar mass, the one that's more linear, the one that has better ability for the molecules to sort of line up with each other and contact each other, that's going to have stronger dispersion forces. Okay? So let's do one other example problem. This one is a much simpler one than that concept. So rank the halogen molecules from lowest to highest melting points. Remember, the halogens are the group 7 elements, which are F2, Cl2, Br2, and I2. These are all nonpolar. And again, we're talking about melting point here, but whether we're talking about boiling point or melting point, we're talking about boiling point in the last one. This one's melting point. The stronger the intermolecular forces, the higher those will be. So stronger intermolecular forces correlates with a higher melting point. And as we just said, London dispersion forces, which is all these are going to have if they're nonpolar, are stronger when you have heavier elements. And so that means, just like in the noble gases, the ranking of the halogens, either from boiling point and melting point, would be from lightest to heaviest. So F2 is going to have the lowest melting point, followed by Cl2, followed by Br2, followed by I2. Or same thing, whether this is melting point or boiling point, would be the same trend. All right, so for most classes of substances, it's relatively simple. You just have to look at molar mass, and the one that's heavier molar mass has stronger intermolecular forces, particularly when we're talking about London dispersion forces as the only ones. All right, so if we have nonpolar molecules, we only have these London dispersion forces present, but once we get into polar molecules, we start introducing new types of forces, and one of them is called dipole-dipole forces. All right, and to give you sort of a context, these are about 1% as strong as a bond, so they're still pretty weak compared to a covalent bond. but they're not insignificant, and they're very important for a lot of substances. All right, so dipole-dipole forces are going to be present in any polar covalent molecule. All right, so we talk about for London dispersion forces, those are the only forces if you have a nonpolar substance. If you have a polar compound, they're going to also have dipole-dipole forces. So they still have London dispersion forces, that's always there, but in addition, they have dipole-dipole forces. And keep in mind that this refers to net molecular polarity. So we learned in chapter 4 how to decide whether a molecule is polar or nonpolar. So it has to be the whole molecule is polar, not just individual bonds. All right. So we're talking about net molecular polarity, not just having polar bonds. All right. Because as we saw in chapter 4, when we talked about molecular polarity, it's possible to have polar bonds but still be a nonpolar molecule. So to have dipole-dipole forces, the whole molecule itself, the molecular polarity has to be non-zero. Okay. So how does this work? For a simple drawing, let's look at the molecule HCl, which is also diatomic. And in this molecule, we should recognize that we have different electronegativities between hydrogen and chlorine. So chlorine is more electronegative than hydrogen, so this is going to be a polar substance, and you're going to have a partial negative on chlorine and a partial positive on hydrogen. And in this case, it's a permanent dipole. So the average electron density in this case is not symmetric. It's going to be sort of tilted in this way, with more electron density in your chlorine, less electron density in your hydrogen, and sort of this net dipole as we call it. All right, and so then these molecules, because they have this partial positive and partial negative, they can line up with other molecules that are arranged in the opposite direction and interact with the opposite charges attracting each other. So if we have another molecule like this that has a partial negative and a partial positive, there's going to be attractive interactions between those. Again, opposite charges attract each other. You can have sort of these side-to-side interactions. You can also have head-to-head interactions where HCl will come in like this. You have a partial positive, partial negative. So especially in condensed phases where you have liquids or solids of these types of compounds, you can have these sort of complex network of interaction with dipole-dipole forces going in all directions. So another one like this, where again, as opposite charges lining up with each other, opposite dipoles lining up with each other and interacting in all these different ways. So all these blue lines are going to be what are called the attractive forces, because again, they're opposite charges interacting. We should also recognize that there's going to be repulsive interactions between the dipoles that are the same orientation. So the delta positives are going to, sorry, I should do that different color, that's what I'm trying to do. There's going to be repulsive interactions between the ones that are the same as well. And so one thing we'll get to later on in the course is that when you have these condensed phases, so the red ones are going to be repulsion. When you have these condensed phases, the molecules are going to sort of line themselves up in a way that maximizes the attractive interactions and minimizes the repulsive interactions. So you have both, but the molecules are going to line themselves up in a way so that the oppositely charged dipoles are closest to each other and able to attract to each other, and the negatively charged ones the same charges, the two positives and the two negatives, are as far away from each other as possible. So we'll get to the structure of condensed phases later on where that becomes more important. But keep in mind that you still have both types of interactions, attractive and repulsive, but in that you have attractive interactions that are going to result in these molecules being held together more strongly than they would if these types of forces were not there. All right? And then the last type of intermolecular force, it has its own category, but it's really just a special type of dipole-dipole force, is called hydrogen bonds. And what's special about it is that it's particularly strong type. So we said that dipole-dipole forces are around 1% as strong as a typical covalent bond. Hydrogen bonds can be about 5 to 10 times stronger than that. So about 5 to 10% as strong as a bond. All right, so again, they're much weaker than covalent bonds, but they are stronger than a typical dipole-dipole force. All right, so hydrogen bonds are a particularly strong dipole-dipole interaction, so they're no different in that regard. They're just partial positive, partial negative charges attracting to each other, but these are particularly strong, and I'll get into the reasons why here in a second. They only exist in certain types of compounds. We're going to have to recognize when that is. All right, so when do you have hydrogen bonds? You're going to have whatever molecule you're considering. There's still covalent compounds that we're dealing with here. But if you have an HF bond, an OH or HO bond, or one or more NH bonds. So if they have one or more of these bonds in the molecule, these are going to exhibit hydrogen bonding. All right, and again, in all of these cases, you have a partial positive on all right, so if your molecule has at least one bond between either fluorine, oxygen, or nitrogen with hydrogen. Now keep in mind, this is where people get confused often. The hydrogen bond is not the covalent bond between oxygen, hydrogen, or nitrogen, hydrogen, but it's the type of intermolecular force that exists when these types of compounds, when these types of molecules interact with each other. So examples of this would be, of compounds that would exist hydrogen bonding would be HF. Water is the classic example of a substance that hydrogen bonds. Alcohols as well, so CH3OH, anything that has this OH group on it, or ammonia NH3, which has 3 NH bonds. All of these will exhibit hydrogen bonding. And again, the hydrogen bonding is not the covalent bond between the nitrogen and the oxygen or whatever in hydrogen. It's the type of intermolecular force that exists between these molecules. And the reason that it's particularly strong is that it is really just a dipole-dipole force. So it's exactly what we drew on this page with partial positive, partial negative charges interacting with each other and attracting to each other. But it's strong for two reasons. One is that, remember that nitrogen, oxygen, and fluorine are the 3 most electronegative atoms on the periodic table. So if you have a hydrogen bonded to that, that's going to be the most polar type of bond that involves hydrogen. So these bonds are more polar, which means they have a larger delta plus and a larger delta minus charge. So that gives a stronger dipole in these cases. And also, hydrogen is really tiny. It's the smallest atom on the periodic table. So in these types of compounds, they can line up really close to each other, pack really close to each other to form these types of hydrogen bonds. And as with any sort of charge-charge interaction, the closer they get to each other, the stronger the interaction is. So for two reasons, both the polarity of the bond and the fact that hydrogen is very small and these molecules can pack together really tightly, you have a particularly strong type of dipole-dipole interaction. So it is classified as a separate type of interaction. Hydrogen bonding versus dipole-dipole forces are sort of two separate categories in our lexicon, but at the same time, the mechanism of them is the same. It's just permanent dipoles interacting with each other. Now, the last ones that I'll touch on, but are not going to be a big emphasis in homework and test questions, but you'll get more details about these a little bit later on in this chapter for some of them, and also in Chem 2 when you take that one. So we have forces involving ions. So the previous 3 that we talked about are forces involved in primarily covalent molecules, so neutral compounds involving nonmetals. But if we have ions involved, we also have some types of forces that could be classified as intermolecular forces as well. So you have ion-ion forces as one of them. These are the types of forces that hold ions together in ionic crystals. These are classified more as a bond. We called this in the past ionic bonding. So this is kind of a gray area. Is this a bond, or is this an intermolecular force, or is it both? Typically we think of this more as a bond than as an INF, but sometimes it gets sort of lumped in the same category. Because again, it's a type of force that results in individual, in this case ions, not molecules, but individual molecules being held together in a condensed phase through these ion-ion interactions. This again is a purely charged-charged Coulombic interaction, so it's very strong. And so if you had sodium plus and Cl minus arranged in a crystal, you have this strong attractive interaction between the two because of the opposite charges. But like I said, it's sort of ambiguous whether we classify this as an ionic bond or an intermolecular force, so we're not really going to put it in that same category in this course, but just be aware that it's there. And then one that you'll talk about a lot in Chemistry 2, if you take 1332, is that you have what are called ion-dipole forces. So the name pretty much gives it away. These are interactions between ions and polar molecules. And these are especially prominent in aqueous solutions. So in this chapter, chapter 9, we're going to only talk about condensed phases that are pure substances, so one element, one compound, and not mixtures. But in Chem 2, you will talk about, in chapter 10, I believe it is the first chapter you'll cover in Chem 2, you'll also talk about these types of things in solutions, in mixtures. And so one prominent thing that you have in solutions are these ion dipole forces, where if we dissolve sodium chloride in water, and we talked about this a little bit when we introduced the concept of aqueous solutions, you have water molecules in the solution which are polar, as we know, delta plus, delta minus. And then the delta minus on oxygen is going to interact with the sodium ions, and this is what's responsible for dissolving the ions and actually bringing them into the solution. And then similarly, if we have water molecules with their partial positive, partial negatives, those can interact as well with the anions of Cl minus. So these types of forces are responsible for the formation of aqueous solutions. As I said, that's not going to be a topic we deal with in any more detail in this chapter, but I just wanted to sort of be complete and make you aware that there are other types of intermolecular forces that are prominent in different types of substances, but the first three that I introduced, the London dispersion, the dipole-dipole, and the hydrogen bonds, are the three that we're going to primarily deal with in this chapter. All right, so then what we can do is we can rank the intermolecular forces from strongest to weakest, or I guess weakest to strongest, we'll do it that way. And they're exactly in the order that I gave them to you, and I kind of already let the cat out of the bag a little bit in this regard. But we have all these different types of intermolecular forces, and we have dispersion being the weakest. So in a substance that's nonpolar, where you only have London dispersion forces, you have comparatively weak intermolecular forces. If you have polar molecules, those are going to have dipole-dipole forces, so those would be stronger intermolecular forces. And then if we have hydrogen bonding, that's the strongest of the three that we're going to primarily deal with. So I think I'll just leave it at that. The ion dipole and the ion-ion forces are even stronger than these, but we're not going to really consider them in this class in that context. So we'll just primarily be responsible for ranking these three. So a lot of the problems that you'll see on this week's homework assignment are going to involve you being able to predict which type of intermolecular forces are present, and then being able to rank certain properties of those substances, be it phase change or other things, based on those types of comparisons. All right? So a typical problem you might see, before I do the sample problem, any questions on these intermolecular forces in general? All right, so the typical type of problem you'll see then is, let's say we give you two substances, CO2 and COS, and we want to know which has the higher boiling point. So again, you have to think about first what types of intermolecular forces are present. The one that has the stronger intermolecular forces is going to have the higher boiling point. So you have to first think about what type each of them has, and then figure out which one of those is stronger. So if we do CO2 first, we've drawn the Lewis structure of CO2 several dozen times in this course already, and we should know by now that it's a linear molecule. All right. So we talked about CO2. This is one of the first ones we talked about when we were introducing polarity, is because we have polar bonds. We have delta minus on oxygen, which is more electronegative. We have delta plus on carbon on each side, but the net dipole is zero because they cancel out. All right, so remember from way back in chapter 4 now, if we have a linear molecule, it's going to be nonpolar because the two dipoles cancel each other out if they're the same. Two carbon-oxygen dipoles, but they're equal and opposite in direction, so they cancel out. CO2 is a nonpolar molecule, so that's the result of that. And because it's nonpolar, it only has one type of intermolecular force, which is London dispersion forces. All right? So as I said, when we're making these types of comparisons, we need to think about what is the strongest intermolecular force that's present in that substance. That's going to be the one that's dominant. In this case, the only intermolecular force is London dispersion force, so that's going to be the strongest for CO2. So that's the only one present. It's the only force present in CO2. Now if we go to COS, it has a very similar structure, still linear, but this time though we have partial negative on oxygen. The carbon-sulfur bond is pretty much nonpolar. There's a slight difference if you remember. So if we go to the periodic table, remember that this one's, let's see, where's the periodic table? There. So if we go to the periodic table, we're talking about carbon-oxygen and a carbon-sulfur bond. So carbon-oxygen is clearly polar, as we said, because oxygen is to the right of carbon, so it's more electronegative. Carbon-sulfur, the sulfur is less electronegative than oxygen, so the difference between carbon and sulfur is smaller. I think sulfur is still a little bit more electronegative than carbon, but it's a very small difference. And so what that means is that we have two unequal dipoles. So even though we have this situation with delta minus, delta plus charges, the dipole that points towards carbon-oxygen is much larger than the dipole pointing towards carbon and sulfur because of the greater difference in electronegativity. So this molecule, and this is going to be true anytime we have a linear molecule with two different outer atoms, this is going to be a polar molecule. So we have a net dipole pointing from left to right, as I've drawn it here. Because these two dipoles, even though they're opposite in direction, they don't completely cancel each other out because one's bigger than the other. The carbon-oxygen bond is more polar than the carbon-sulfur bond. So this molecule is polar, and because it's polar, it has two types of intermolecular forces. It's still, of course, going to have London dispersion forces, but it also has dipole-dipole forces. Sorry, one more dipole. So this has dipole-dipole forces as well. This is the stronger one, so this is the one that we're going to focus our attention on as being the most important one for this molecule. And because this molecule has dipole-dipole forces, whereas CO2 only has London dispersion forces, this would have stronger intermolecular forces, and this is going to then have a higher boiling point. All right, so if you're comparing a polar and a nonpolar molecule, unless they're way different from each other, you would expect the polar molecule to have a higher boiling point because it has stronger intermolecular forces. So dipole-dipole forces are always stronger than London dispersion forces. Because we have those in COS, we're going to have the expectation that this would have a higher boiling point. And that is indeed true if you look up the values. Okay, so any questions on this one? All right. Now we're going to also talk about some other properties of liquids then that result from these intermolecular forces that are dependent on them. We're not going to actually say a lot about liquids in this class, so the next, 2 or so slides that I give you is basically the only thing we're going to talk about with liquids in this entire course. There's not as much to say, and one of the reasons is that liquids have pretty irregular structures. There's not much we can say about them besides some of these key properties that we're going to talk about. All right. So one thing that we have in liquids is called surface tension. So this is basically what we want to be familiar with these definitions and then be able to use intermolecular forces to predict whether these are going to be stronger or weaker in certain substances. All right, so surface tension is the resistance of a liquid to increase its surface area. And basically, this is the property that gives liquids an upper surface. So this is why they don't just fly off into the gas phase. They actually have an upper surface. And this surface tension can be significant in some cases. I think it's even possible in the right situations to float a penny on top of water because of the surface tension. You have to be really careful and have the right setup and everything. But because of this surface tension, things that would normally sink in water can actually sit on the top of the water because there's this tension at the very surface. Once you get into the water, then you don't have that anymore. The reason that surface tension exists is because basically, remember, we have these intermolecular forces that are holding all the molecules together. And so at the very top of the liquid, at the very surface, you don't have intermolecular forces in all directions because you don't have any molecules above the surface. So in those cases, all the intermolecular forces are pulling the liquid down at the very surface. You don't have them in all directions at the surface. And that downward net pull is what keeps that surface sort of rigid and has that surface tension associated with it. So again, we don't have to worry too much about the details, but we should be familiar that surface tension is one property of liquids that's caused by intermolecular forces. And then the other one is called capillary action. This is the spontaneous rising of a liquid in a glass tube. So this is pretty easy to do. If you guys ever use the disposable glass pipettes in chemistry lab? Yes? So if you take one of those glass pipettes and you just dip the tip into water, there's going to be a little bit of, or any liquid really, there's going to be a little bit of that liquid that just rises up into the pipette without you even having to put any suction on it. So that's what's called capillary action. It's a liquid rising through a glass surface. And the reason that we have capillary reaction is because of what's called adhesive and cohesive forces. All right. So the adhesive force is the force of attraction between the liquid and its container. And typically we're talking about glass containers, especially when we're dealing with capillary reaction and some of these other things that are related to that. So keep in mind that glass is polar. The surface of glass has a lot of OH groups on it, like sort of hydroxide kind of things on it. So it's able to hydrogen bond with liquids that are able to do that. So you have a polar surface in your glass, and then if you have especially a polar liquid, you're going to have relatively strong interactions between the liquid and the glass. And then the other type of force is the cohesive force, which is just the intermolecular forces of the liquid itself. So molecules in the liquid interacting with each other. All right. So then when you have a liquid in a glass container, you have the possibility then of having convex or concave what are called meniscus. So the surface of the liquid is not typically going to be perfectly flat. It's going to be curved either up or down. So concave, the way to remember that is that it's caving in. So it's a concave surface, whereas convex is the opposite, where it's sort of bowed out in the other direction. So what happens in this situation is basically you have different relative strengths of the cohesive and adhesive forces. So if you have a convex meniscus, basically the glass is pulling on the liquid, the liquid is pulling on itself stronger than the glass, and so in this case the cohesive forces are stronger than the adhesive forces. And then for a concave meniscus, you see that the liquid is starting to creep up the sides of the container here and form this sort of, as I said, U-shaped or concave meniscus. And that's because in this case you have particularly strong adhesive forces where the glass wants to start rising up the sides of the liquid wants to start rising up the sides of the glass to make those interactions stronger. And so in this case your adhesive is stronger. So these are just very basic concepts. We don't really want you to know them at very deep levels, but just some definitions associated with liquids and things that are related to these intermolecular forces. All right. And then one thing that's true about all of these is that they all correlate with intermolecular forces. So the stronger the intermolecular forces, you would expect the surface tension to be larger. Okay, so surface tension is how much tension you have on the surface, how resistant it is to changing a surface area. So the stronger the intermolecular forces, the higher the surface tension. And similarly, especially for these cohesive forces, the stronger the intermolecular forces, the stronger these cohesive forces will be. They're all related to each other. The other major property of a liquid is called viscosity. And viscosity is the resistance to flow. And you can think of it more in less technical terms as how thick the liquid is. I'm not talking about its body shape. I'm talking about its as it pours, whether it freely flows or is more like syrup, like this one here. So I think this is probably like a motor oil and then water with food coloring in it, so you can see it better. And so the one on the left has relatively low viscosity. It pours out very easily, whereas this liquid on the right, which pours out very slowly, we would say has high viscosity. So viscosity is basically how thick the liquid is when you try to pour it. It's resistance to flow. And just like these other properties, the stronger the intermolecular forces, the higher the viscosity that you typically have. Okay? All right, so stronger IMFs refers to higher viscosity, and that's, again, a correlation that's pretty easy to draw based on the types of substances. So if we give you an example and ask you to predict which of these liquids has the highest viscosity, you just have to rank their intermolecular forces in terms of which one is stronger or weaker. All right? So if we look at this first one here, this hydrocarbon, which is called pentane, N-pentane, CH3, CH2, 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 CH3. Remember a shortcut that I told you earlier that's helpful to remember in this section is that anything that's a hydrocarbon, where carbon and hydrogen are the only two elements, those are always going to be nonpolar. The reason is basically because you have no lone pairs in these structures. So remember, in any structure that has no lone pairs, you don't have any possibility of having polarity if all the atoms are arranged in that way. So we have nonpolar molecules anytime you're dealing with hydrocarbons. And so because it's nonpolar, the only intermolecular force you have is London dispersion forces. All right, so for this molecule, London dispersion is the only type of intermolecular force you have. If we go to the next molecule here, it's not terribly obvious from the way that I've drawn the structure, but remember back in, now to chapter 3, chapter 4, when we talked about molecular structure, if you have an oxygen here in the middle, it's going to also have two lone pairs on it. So this central oxygen atom is going to be bent with the two carbon chains coming off of it. Move this so I can draw this better. All right, so that's London dispersion, and then this molecule, the central oxygen is bent. It has two lone pairs on it, so it's going to be a bent molecule. And you're going to have these carbon chains coming off. And so because it's a bent molecule and because the carbon-oxygen bonds are polar, this would be a polar molecule. Now, key question here, does this molecule have any hydrogen bonding involved in it? I heard a yes. Anybody care to disagree? I care to disagree. So the reason this doesn't have hydrogen bonding is because, remember, for hydrogen bonding, we need to have a hydrogen bonded directly to the oxygen. In this case, the oxygen is bonded to the carbon atoms. Remember, when we write structures like this, CH2, the two hydrogen atoms are bonded to the carbon that comes before it. So there's no bonds between oxygen and hydrogen, so there's no hydrogen bonding. This is still a polar molecule, so it's going to have dipole-dipole forces, but it won't have any hydrogen bonding. Then finally, in the last molecule here, without even thinking about in detail what the shape of it is, we see very clearly that there are two OH bonds in this molecule. All right, one at each end. So this has hydrogen bonding involved. Anytime you have hydrogen bonded to oxygen or nitrogen or fluorine, you have hydrogen bonding interactions as intermolecular forces. This is going to give us the strongest intermolecular forces of these three. And this molecule then would be the one that you expect to have the highest viscosity as a result. So these three molecules have, very similar molecular weights, very similar shapes, but because this one has the strongest intermolecular forces, you'd expect it to have the highest viscosity or to be the thickest liquid. And this liquid is called propylene glycol, and it is it's one of the components, or very similar to one of the components that's in windshield washer fluid, and it's significantly more viscous than water is itself even. So you can predict viscosity as well by using the intermolecular forces. So that's all we're really going to say about liquids. The vast majority of Chapter 9 that we're going to cover from now on deals with solids and sort of different categories of solids, different structural aspects of them, some different properties as well. There's going to be a lot more in depth that we're going to go into with solids as we'll see. So the first thing we're going to do is we're going to classify solids into two major categories, amorphous and crystalline. Okay? So amorphous solids are solids that have no regular structure. And because amorphous solids have no regular structure, there's not a whole much else we can say about them in this course anyway. Okay? So there's a whole field of chemistry devoted to studying amorphous solids, but it's not really easy to say much about it because there's no regular structure. So essentially what you have in an amorphous solid is they're made up of atoms or molecules, but the atoms and molecules are sort of randomly arranged. There's no regular repeating structure to them. There is an example from your everyday lives that you're very familiar with, which is glass. So any glass that you use to make a window or whatever is an amorphous solid. So it's a solid, as you can likely tell very easily, but it doesn't have a regular repeating structure, no predictable structure that you can really define in any clear terms. So that's what we mean by amorphous solid. The type that we're going to talk about a lot, though, and we're going to talk about two major categories of them especially, are called crystalline solids. And these are solids where the components are arranged in a very regular fashion, in a repeating fashion as well. All right, what I mean by periodic fashion is that you have units that repeat themselves over and over again as you go through the entire structure. So we'll talk about, for example, the structure of ionic compounds later on. And if you have sodium chloride, you're going to have, in all directions, you're going to have sodium chloride, sodium chloride, sodium chloride, all directions lined up in that way. So you have these sort of regular repeating units that occur over and over again in this crystalline solid that are, as you go in every direction, you have a very predictable arrangement of all the components, a very regular arrangement that you can define very easily. So how we sort of classify these is what's called a lattice. So the lattice is the 3D system of points and typically in chemical compounds, each point represents an atom or molecule in the crystal. So it's the three-dimensional system of points that defines that crystal, and each of those points is an atom or a molecule. Again, they repeat themselves in 3 dimensions in very regular ways that we're going to learn how to start defining for certain categories of substances, relatively simple ones in this course, obviously. Now, you actually, in a non-chemical sense, you have some familiarity with lattices in your everyday life. Especially 2-dimensional lattices are common. So if you've ever seen, either a carpeted or a tiled floor that has a regular pattern on it that repeats itself over and over again, that series of points that makes up that pattern could be considered as a lattice. In that case, 2-dimensional, but chemical compounds would have 3-dimensional lattices where you have these points that repeat themselves over and over again in all directions. The points in this case are going to be atoms or molecules that make up whatever compound it is you're talking about. And that's what we mean by lattice, is that sort of system of points. Now, how we usually define crystalline solids, though, is not by thinking about the entire lattice, because the entire lattice goes on forever and ever in all directions. We think about what's called the unit cell. And this is the smallest repeating unit in a crystal, but it's a little bit more specific than that. It's the smallest repeating unit that can generate the crystal via translation. All right, and I'll tell you what that means here in a second. So talking and writing at the same time, not going well today. So it's the smallest repeating unit in a crystal, and the lattice then is generated by taking the unit cell and translating it in all directions. So you can think about, basically, one way to think about this is, imagine that a crystal is the world's most boring Lego set, where you have just one type of block, and that's your unit cell, and then you generate the lattice by taking that unit cell and stacking it in all 3 directions. So you line them up this way, this way, this way, you stack them up on top of each other, you line them up in the 3rd direction, and just repeating that same thing over and over again. So translation is basically just taking that unit cell and just moving it in each direction, repeating it over and over again in each direction, and that combination then generates the lattice. So we always think about the unit cell then, because as we'll see, the unit cell is going to have a very specific structure associated with it, and we can make some predictions about the properties of that solid based on some of the aspects of the unit cell that we can easily characterize. So that's kind of the basic definitions. We'll get into this structural chemistry a little bit more next time, so we're going to leave that behind for now. What we want to talk about at the beginning then are types of crystalline solids, and really only for 2 of these types are we going to really define the structure in any level of detail. So one type of crystalline solid is an atomic solid. And this is, as the name implies, made up of just one type of atom. So basically, the examples of atomic solids are just about every element that exists as a solid on the periodic table, especially especially ones that are not polyatomic. So anything where the standard state of the element is just the element by itself and it's a solid. So things like carbon, which one of those is going to be diamond, is an example of an atomic solid, which is just pure carbon. Or most metals on the periodic table, excepting mercury, which is a liquid. Most metals exist as atomic solids, where you have regular arrays of those metal atoms arranged in all three directions to give you that solid. So most metals are classified as atomic solids, and we will talk about the structures of metals starting next time. The other category that we'll talk about a lot are ionic solids, where again you have different ions, this time plus and minus ions as the lattice points. So in atomic solid, the lattice points are just the individual atoms. In ions, you have two different types of lattice points. You have positive and negative ions that repeat themselves over and over again. And we saw this, basically any ionic compound that we could think of is going to be classified as an ionic solid in this crystalline form. So sodium chloride, you've obviously seen that salt makes pretty nice big crystals. So that crystal is made up of regular repeating units of sodium and chlorine, which is what's shown up here. We'll talk about that in detail later on. And then we have, zinc sulfide is another common ionic compound with a pretty regular structure, magnesium chloride, etc. So basically any ionic compound you can think of, and in this course we're going to talk about a few categories of binary ionic compounds and what their structures look like as well. And then the last type, which we're not going to talk about in detail from a structural standpoint, but is still very important, are called molecular solids. So these are made up of covalent compounds. So anytime we have a covalent compound that exists as a solid, and it's a crystalline solid in particular, we would expect this to be a molecular solid. So the individual components, the lattice points, are molecules in this case. And the molecules are held together by intermolecular forces. All right, so again, in these cases you have the compound exists as molecules, or the element in some cases exists as molecules, but those molecules are held together in a regular pattern to give you a molecular solid. So examples of this would be things like iodine, I2, so it's a diatomic molecule, but it exists as a solid at room temperature, so it would be classified as a molecular solid, where you have I2 molecules arranged over and over again in 3 dimensions to make that crystal. The one that we see most often in our everyday lives is ice. So when you form ice crystals, you have water molecules that are held together by hydrogen bonding, and those water molecules repeat themselves in regular ways to give you that crystalline structure. All right. So the first, any questions on sort of these classifications? Again, we're going to get more information about all of them as we go through, but anything right now that you want me to clarify before I get into the first type? Yes? So the question was, does temperature come into account for molecular solids? So yes, they will only exist as a molecular solid at a low enough temperature below the melting point. So, water would not be a molecular solid when it's a liquid, but when you freeze it and cause it to crystallize into those ice crystals, then it would be called a molecular solid. So it has to be in that right temperature range to be existing as a solid. But anytime that's true, it could, as long as it's crystalline, it could be classified as a molecular solid in those conditions. Yes. Anything else? All right. So the first type we're going to talk about are metals. And before we talk about their structure, which we'll get to next time, we're going to talk about the sort of the bonding model in metals. We've classified bonds as 2 major types so far. We have ionic bonds and covalent bonds. We saw that back in chapter 3. There's one other type of bond that we now need to think about when we're talking about metallic solids, which is a metallic bond. All right. And this is kind of hard to draw out in any level of detail, but the picture that sort of is often used to rationalize this is called the electron C model. All right. So imagine we have a group 1A element. All right, so thinking now back to some things we should have learned back in chapter 3. So group 1A is the first column of the periodic table. How many valence electrons do they have? And in a metal, is the valence electron relatively easy or relatively difficult to remove, to ionize? Relatively easy, right? So anything on the left side of the periodic table you can ionize relatively easily. So when group 1A metals arrange themselves into these regular metallic solids, you have those valence electrons are very loosely held. And so you can almost think about this picture as you form +1 ions, so that valence electron again being loosely held by the individual atoms. So you form these positive ions that arrange themselves. And then you have what we refer to as a sea of electrons that holds them together. So let's see if this is the right pen to use. So basically the valence electrons are not bound to any one atom, they're delocalized over all of them. So they're kind of just this amorphous sea of electrons, which I'll just indicate with a yellow blob here, that just delocalizes over all the atoms in the structure. So they're not tightly held by one atom, they're not shared between two atoms, they're just moving around all over the place across the whole structure of the metal in all directions. So the valence electrons in this case are very loosely held, so I'll write that out here. This yellow that I'm drawing is what we refer to as a sea of electrons, which is the valence electrons that are loosely held and they have really high mobility, they're able to move around the structure. And so in metals, all valence electrons are loosely held and delocalized. All right, so that's what we mean by the sort of sea of electron model. And then if we go to, let's say, a group 2A element, the picture would look a little bit different. So in group 2A, they have two valence electrons, so they have two loosely held outer electrons each. So we can think of these as being an arrangement of 2+ cations in group 2A. So we have 2+ cations where the two valence electrons are again loosely held and floating around all of the atoms, not bound to any single atom or any pair of atoms. All right, so it's a little bit different type of bonding model because we no longer think about electrons being shared between two atoms, but really electrons are delocalized over all the atoms in the entire structure. Now, if we had to think about this, what would we think would be a stronger metallic bonding interaction? Group 1A or Group 2A? Group 2A, because in Group 2A we have two valence electrons that are delocalized and sort of 2+ cations that are left behind, so we have more charges interacting with each other, stronger interactions as a result. All right, so that's what we mean by that's sort of our model. So let's talk about some properties related to this then. So in general, the melting points of metals are moderate to high. So they have, as we said, reasonably strong interactions, so you typically heat them up to melt them. They're not as high as some other substances, though, especially ionic compounds, because if you have a liquid metal, you can still have those types of metallic bonding interactions. Even though there's not a regular structure in the liquid, you can still have the delocalized electrons, you still have atoms largely in contact with each other, and so they're still, you don't have to break all those interactions basically to melt the substance. So they're moderate to high, but they're not ridiculously high for most metals. The more important thing to characterize is how do we compare melting points among different types of metals. So as we go across a period, that would be left to right on the periodic table, specifically comparing group 1 and group 2 as we did in the last slide. As you go across, the melting point increases because you have more valence electrons that are now involved in the metallic bonding. So you have higher charge or more delocalized electrons, which causes stronger interactions between those metal atoms and holds them together more tightly. All right, so remember, to melt a substance, we're going from solid to liquid, so we have to disrupt at least some of those metallic bonds to be able to take the structure from the solid and melt it into a liquid. So as you go across a period, so if we compare lithium to beryllium, which are right next to each other on the periodic table, lithium has a much lower melting point than beryllium. Okay, so that's how we compare them. Then if we go down a group, which is again same column periodic table now from top to bottom, the melting point decreases. All right, and this is again because as we go down the same column in the periodic table, they all have the same number of valence electrons. If you if you're comparing all the group 1A elements, they would have one valence electron delocalized. If you have group 2A, you'd have two valence electrons delocalized. But as you go down the periodic table, the metal cations that are left behind that are held in place by these metallic bonds are getting larger and larger, and because they're larger, you have weaker attractions to the electron C. All right, so a concept we saw when we talked about lattice energy is that as you increase the size of a cation, you weaken the charge-charge interactions, and the same thing is true for pure metals as well. As you increase the size of the metal atom, you still have the delocalized electrons that are involved in metallic bonding, but the attraction of those delocalized electrons to the metal nucleus that's left behind sort of weakens, and that weakens the metallic bonding and makes the melting point lower as you go down. So basically the melting point correlates with how strong the metallic bonds are. The stronger the metallic bonds, the higher the melting point will be. And then boiling points for metals are, as it turns out, very high. So it's relatively easy to melt most metals, so you don't have to go to ridiculously high temperatures. We can do that, obviously industrially, that's very important to melt in metals in all different settings. But to boil a metal is extremely difficult because in order to boil something, you have to separate all of the atoms from each other into the gas phase. Remember, boiling is going from liquid to gas. And it's difficult for those metal cations that are left behind from the delocalized electrons and the valence electrons that are associated with them, it's difficult for them to separate from each other and completely break those metallic bonds. All right, so as we said many times in this course, you have attractions between positive and negative ions are very important in really all of chemistry. Between positive charges and negative charges in general are very important. In order to boil a metal, you'd have to break all those attractions between electrons and protons, and that's hard to do. So boiling points for metals are very high, even though they're relatively easy to melt in general. All right, other properties of metals that are caused by this electron C model is that we talk about their mechanical properties. So this is basically how hard a substance is, how easy it is to change the shape of the substance, how easy it is to bend and break, and all those stuff. That's referred to as mechanical properties. And metals in general are what we call malleable. Which is a fancy way of saying bendable. All right, so I'm sure some of you in a random feat of strength throughout your life have taken a piece of metal and bent it and shown how jacked you are by doing that, and that's true of most metals are able to be bent. Some are harder, more difficult than others to bend, and all that. But that's a property that's pretty general for most types of metals, and the reason is that even though you have this metallic bonding, the metal ions are not held in place too tightly. And they can slide through the electron C. So this sort of deformation of metals that you can bend them without breaking them is because the metal atoms have a little bit of flexibility and a little bit of ability to sort of move through that electron C and deform and still not completely disrupt that metallic bonding. It's different with ionic compounds, as we'll see later on, because in those cases the charge-charge interactions, the interaction between the positive and negative ions are very directional. And so if you try to bend an ionic compound, you end up breaking those apart completely, as opposed to metals, which you can bend because there's a little bit of flexibility in the structure that you don't have with other types of substances. So regardless of whether the origin is clear or not, we should be familiar with the fact that metals are malleable, so that's one key characteristic of them. And then electrical and thermal conductivity, as you're likely already aware from other contexts, metals are very good at conducting both heat and electricity. All right, so metals are good for both thermal and electrical conductivity. Both in the solid and the liquid states where you have this significant metallic bonding present. And especially for electrical conductivity, it's pretty obvious why. It's because the electrons are mobile in metals. So because we have these loosely held valence electrons that are delocalized in the metallic structure, passing electrons through a metal is relatively easy to do because they can just move through that sea of electrons, move through that structure without much impediment to doing that. So again, one of the things we're doing in Chapter 9 is classifying different types of substances and their properties. And for metals, you should be aware that they have, as we said, moderate melting points, they're malleable, and they're good conductors. And if you know those three basic things, that's really the level of depth we expect you to understand for this part. Next time, though, we're going to get into the structures of metals, which is something a bit different than we've seen before. So hopefully we'll have fun with that as well, and I'll see you on Monday.